There's a silence out there, a vast, echoing silence that stretches farther than any human mind can truly grasp. Picture the deepest ocean, the widest desert, or the highest mountain you've ever seen, and then multiply that emptiness by a number so large it loses all meaning. That's the cosmic void, an endless expanse where stars are mere pinpricks of light, where entire galaxies drift like dust motes in a sunbeam, and where mysteries lurk in the darkness waiting to be uncovered. Tonight, we're not just staring up at the night sky, we're diving headfirst into its most baffling secrets. 25 cosmic enigmas that defy explanation, challenge our understanding of reality, and might just rewrite everything we thought we knew about the universe. Think about the last time you felt truly small, standing beneath a sky full of stars, maybe, or hearing about the sheer scale of a black hole. That humbling sensation is just the beginning. Because out there, beyond the edge of our telescopes, there are forces at work that shouldn't exist, galaxies spinning too fast to hold themselves together. Signals from the void with no identifiable source, strange whispers of dark matter weaving through the cosmos like invisible threads, pulling at the fabric of space itself. These aren't just curiosities, they're clues, pieces of a puzzle so enormous that solving even one could change the course of human knowledge forever. So why does any of this matter? Because the universe isn't some distant, untouchable spectacle. It's alive with questions that tug at the very core of who we are. Are we alone? How did all of this begin? And what else is hiding in the shadows just beyond our reach? This isn't just a tour of cosmic oddities. It's an invitation to stand on the edge of the unknown and dare to look further. By the time we're done, you won't just see the night sky differently, you'll feel it. The void isn't empty, it's waiting, and tonight we're answering the call. Hidden in the darkness between constellations, something massive is pulling at our galaxy, and everything around us with a force we can't ignore. Astronomers call it the Great Attractor, and it's one of the most baffling gravitational mysteries in the cosmos. Picture this: billions of stars, including our own Milky Way, are being dragged toward an unseen point in space like leaves caught in a cosmic river. But here's the twist: we can't actually see what's doing the pulling. This invisible behemoth sits roughly 250 million light-years away, tucked behind the dense stars of our galaxy's equator in a region astronomers poetically call the zone of avoidance. The dust and light from our own galactic neighborhood obscure the view, leaving us with more questions than answers. Some theories suggest it might be a supercluster of galaxies so dense that its gravity bends the universe around it. Others speculate about exotic, unseen matter, something beyond even dark energy, yanking entire galaxies off course. What makes this even stranger? The Great Attractor shouldn't be this powerful. Based on the visible matter we've mapped, its gravitational pull defies all expectations, as if there's an entire hidden layer of the universe we've yet to uncover. It's like hearing the roar of a waterfall just beyond a thick fog, knowing something monumental is there but unable to glimpse its true form. Every new observation deepens the mystery, hinting that whatever lurks in that darkness might rewrite our understanding of gravity itself. So why haven't we solved it? Imagine trying to study a mountain while standing in a blizzard. Our telescopes, even the most advanced ones, struggle to pierce through the interstellar dust shrouding the Great Attractor. Each breakthrough, like detecting faint radio waves from galaxies hidden behind the veil, only adds to the puzzle. One thing's certain: this isn't just a curiosity. It's a gravitational siren call, pulling us toward a revelation that could change how we see the fabric of the cosmos. And the closer we get, the more the universe seems to whisper, there's so much more out there than we ever dreamed. Recent observations have only deepened the Great Attractor's enigma, revealing a cosmic tug of war we're only beginning to comprehend. Cutting-edge radio telescopes like the Parkes Observatory in Australia have pierced through the Milky Way's dusty veil, uncovering hundreds of previously hidden galaxies swirling toward this gravitational epicenter. Yet instead of solving the puzzle, these discoveries have multiplied the questions. The sheer number of galaxies in this region can't fully account for the immense pull we're experiencing. It's as if we've found the visible tip of an iceberg with something far more massive lurking beneath. Some scientists argue we're seeing the fingerprints of the Vela supercluster, a sprawling network of galaxies that might amplify the Great Attractor's effects. Others propose an even wilder idea, that this could be the edge of a gravitational anomaly spanning billions of light years, a cosmic structure so vast it warps the very flow of the universe. Picture a whirlpool in space-time, dragging everything toward its center over epochs of time. But here's where things get strange. Our best simulations of cosmic evolution can't fully replicate this phenomenon. The math simply doesn't add up without invoking unseen forces or rethinking how gravity behaves on scales we've never before tested. The Milky Way itself is part of the problem, not just hiding the Great Attractor from view, but actively complicating our measurements. Imagine trying to map a city skyline while standing in the middle of a blinding sandstorm. That's what astronomers face when observing through our galaxy's crowded plane, where starlight scatters and interstellar dust distorts signals. Even infrared and radio waves struggle to penetrate certain dense regions, leaving frustrating gaps in our data. The upcoming Square Kilometre Array telescope might change that, promising unprecedented resolution to peer through the cosmic fog. But for now, the Great Attractor remains half shadow, half revelation, a reminder that sometimes the universe guards its secrets fiercely. What's most thrilling isn't just the mystery itself, but what cracking it could reveal. If the Great Attractor's power stems from exotic physics, perhaps a flaw in Einstein's relativity or an unknown type of dark matter, it could rewrite textbooks overnight. Or maybe we're glimpsing a fundamental property of the cosmos, that gravity over incomprehensible distances behaves in ways our labs could never predict. Every observation sends ripples through astrophysics, proving that even in the era of James Webb and gravitational wave detectors, the universe still has cards it hasn't shown us. The Great Attractor isn't just pulling galaxies, it's pulling us toward a frontier where today's laws of physics might shatter against tomorrow's discoveries. If the Great Attractor leaves us grasping at shadows, then dark matter is the phantom that casts them, an invisible giant holding the universe together while slipping through our fingers like smoke. Think of every galaxy, every spinning cluster of stars as a carousel. Now imagine that carousel whirling so fast its riders should go flying off, except something unseen keeps them firmly in place. That's dark matter in action, the cosmic glue preventing galaxies from tearing themselves apart, yet utterly refusing to show its face. Scientists estimate dark matter outweighs normal matter 5 to 1, meaning the stars and planets we see are mere flecks of light drifting in an ocean of something far stranger. We know it's there because its gravity bends light around galaxies like a lens, warping the very fabric of space. But when we train our most sensitive detectors on it, silence, no light, no radiation, no particles we recognize, just the gravitational echo of something massive moving in the dark. The hunt for dark matter reads like a detective story where every clue leads to a dead end. Underground labs shielded from cosmic rays listen for the faintest whisper of a dark matter particle colliding with ordinary atoms. Mile-wide particle colliders smash protons together at nearly the speed of light, hoping to create, even for a fraction of a second, a shadowy visitor from the dark sector. Yet decades into the search, the verdict remains: whatever dark matter is, it doesn't play by the rules we've written. Here's what makes this even stranger. Dark matter isn't just hiding, it's sculpting the universe on a scale we're only beginning to map. Supercomputer simulations show that without its invisible scaffolding, galaxies would never have clumped together after the Big Bang. It's the unseen architect of the cosmic web, the silent choreographer guiding where stars will burn and planets will form. Yet for all its influence, it might not even be a single substance. Some theorists argue we're chasing multiple phantoms called dark matter, warm dark matter, even bizarre, fuzzy dark matter behaving like quantum waves on galactic scales. The most tantalizing possibility, we might be asking the wrong questions altogether. What if dark matter isn't just an undiscovered particle but a flaw in our understanding of gravity itself? Modified Newtonian dynamics, or MND, suggests gravity works differently on cosmic scales, eliminating the need for dark matter entirely. But even this radical idea can't explain all the observations, leaving us straddling two worlds, one where we're missing a fundamental piece of physics, and another where 85% of the universe's matter is hiding in plain sight. Every failed detection deepens the mystery. Every new theory stretches the boundaries of what we thought possible. Dark matter isn't just a gap in our knowledge, it's a mirror held up to science itself, showing us how much we still don't understand about the cosmos. And until we crack its code, the universe will keep its greatest secret, that most of what exists doesn't want to be seen. Deep beneath mountains and abandoned mines, scientists have built some of humanity's quietest rooms, chambers so isolated from cosmic noise that they might finally catch dark matter in the act. These underground laboratories, like Italy's Gran Sasso facility or South Dakota's Sanford Lab, exist for one reason: to listen for the universe's shyest particle. Picture a vat of liquid xenon chilled to -100 degrees, watched by sensors so sensitive they could detect a single photon. Now imagine waiting months, even years, for the rare moment when a wisp of dark matter might nudge an atom and reveal itself. That's the painstaking reality of detectors like LUX Zeppelin and Xeno NNT, where researchers have eliminated every possible interference, only to find nothing but eerie silence so far. Meanwhile, at CERN Large Hadron Collider, physicists take the opposite approach, smashing particles together with enough energy to potentially create dark matter on the spot. Think of it as trying to reconstruct an invisible fire by studying the sparks. When protons collide at nearly light speed, they briefly unleash conditions not seen since the Big Bang, potentially birthing exotic particles that vanish before our detectors can catch them. The hope that these fleeting shadows might leave behind fingerprints in the form of missing energy, unaccounted for gaps in the math that whisper something was here. Yet after countless collisions, the machine that found the Higgs boson has come up empty-handed for dark matter, forcing physicists to question whether they're even looking in the right dimension. The frustration mounts because we know dark matter must exist. Its gravitational pull is written across the cosmos. Galaxy rotations, gravitational lensing, even the cosmic microwave background all point to its presence. Yet every experiment designed to spot it directly hits a wall. Some theories suggest dark matter might interact with ordinary matter only through gravity, making it effectively blind to our detectors. Others propose it could be hiding in extra-spatial dimensions beyond our perception, or that we're dealing with not one but multiple flavors of dark particles, each requiring different hunting strategies. What keeps scientists awake at night isn't just the lack of answers, it's the growing suspicion that dark matter might be far weirder than we imagined. Could it be primordial black holes from the universe's first second? A cosmic relic called the action, so light it behaves more like a wave than a particle. Or perhaps sterile neutrinos, ghostly cousins to the neutrinos we know, passing through entire planets like they're not even there. Each possibility demands entirely new experiments, from satellite telescopes scanning for gamma-ray signatures to ultra-precise atomic clocks, measuring subtle time distortions caused by passing dark matter streams. The most humbling realization, after decades of searching, we may have barely scratched the surface. dark matter could be right in front of us, disguised as something so ordinary we've overlooked it 1,000 times. Or it might require technology we haven't invented yet, detectors sensitive enough to hear the universe whispering in a language we don't yet understand. One thing's certain, solving this mystery won't just reveal what's missing from our equations. It will show us an entirely new side of reality, proving once again that the universe always keeps its most astonishing secrets just beyond the light. If dark matter is the universe's hidden scaffolding, then dark energy is the phantom hand pushing everything apart, an invisible force stretching space itself faster than light should allow. Picture the cosmos as a loaf of raisin bread baking in an oven where each raisin is a galaxy. Now imagine the dough suddenly starts expanding at an accelerating rate, not because of heat, but because the oven itself is rewriting the rules of physics. That's the unsettling reality dark energy presents. Empty space isn't just empty, it's brimming with a repulsive energy that defies all expectation. The discovery came in the late 1990s when two teams of astronomers measured distant supernova to gauge the universe's expansion rate. They expected to find gravity slowing things down, the cosmic aftermath of the Big Bang winding toward equilibrium. Instead, they found the opposite. Galaxies were racing away from each other faster and faster, as if some unseen accelerator pedal had been floored. The only explanation, a mysterious energy permeating the vacuum of space itself, now termed dark energy. Here's what makes it so baffling: it behaves like anti-gravity. While matter and dark matter pull objects together, dark energy pushes them apart with a strength that grows as the universe expands, but the paradox runs deeper. According to quantum mechanics, empty space should possess a tiny amount of inherent energy, what physicists call vacuum energy. Yet when they calculate how much energy there should be based on known physics, the number is off by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. It's arguably the worst theoretical prediction in the history of science. Dark energy's observed density is absurdly small compared to predictions, as if the universe tuned this force to a precision beyond comprehension. Some call it the fine-tuning problem, a cosmic coincidence so improbable it suggests either a colossal gap in our understanding or something far stranger. The leading theory, Einstein's cosmological constant, treats dark energy as a static property of space, but alternatives abound. Could it be a dynamic field, like the inflationary force that stretched the early universe, reappearing in a new form, or evidence of extra dimensions leaking gravity into our universe? The most radical proposals suggest gravity itself operates differently across cosmic distances, a twist that would upend Einstein's relativity. What's certain is that dark energy dominates the universe's budget, making up 68% of its total content. It's the ultimate puppeteer, determining whether the cosmos will end in a fiery collapse, a frozen fade, or most likely, a runaway expansion that rips galaxies apart atom by atom. Yet for all its power, dark energy remains ghostly. Unlike dark matter, which bends light and clumps around galaxies, dark energy leaves no direct fingerprints. It's detectable only through its effect on the universe's expansion, a subtle imprint on the largest scales. Upcoming telescopes like the Vera Rubin Observatory aim to map its influence with unprecedented precision, hunting for patterns in billions of galaxies. But until then, we're left staring at the biggest question in cosmology. Why does the void push back? The answer might not just redefine dark energy. It could reveal whether our universe is one of many in a bubbling multiverse, or a single, inexplicable anomaly where the rules were written just right for us to exist. Every measurement, every failed theory brings us closer to a truth that might shake physics to its core. Dark energy isn't just accelerating the universe, it's accelerating our realization of how little we truly understand. The cosmological constant feels like a cosmic shrug, Einstein's famous greatest blunder. That might have been his greatest insight all along, when he first added this mathematical fudge factor to his equations in 1917. It was meant to balance the universe against collapse. Later, after Hubble discovered the cosmos was expanding, Einstein tossed the idea aside. But now, with dark energy accelerating that expansion, the constant has staged a comeback as the leading explanation. Imagine space itself as a stretched rubber sheet. The cosmological constant suggests every cubic inch of that sheet, no matter how empty, contains a fixed amount of repulsive energy like invisible springs pushing outward. Simple, elegant, yet utterly perplexing. Why does this energy have the precise, minuscule value needed to allow galaxies to form without tearing them apart immediately after? Quintessence offers a twist, a dynamic dark energy that ebbs and flows across cosmic time. Named after the ancient fifth element believed to fill the heavens, this theory paints dark energy as a field that could clump like syrup in some regions while thinning elsewhere. Unlike the stubborn cosmological constant, quintessence might interact with matter, even decay over epochs. Picture a universe where dark energy was stronger in the past, shaping how galaxies clustered, then weakened just enough for life to emerge. Some models even suggest it could flip signs one day, switching from repulsive to attractive and triggering a big crunch collapse. But here's the catch. We've found no direct evidence for quintessence's variations, leaving it suspended between mathematical elegance and observational silence. Then there's the phantom energy scenario, dark energy growing stronger as space expands, a runaway feedback loop with apocalyptic consequences. In this model, the repulsion doesn't just push galaxies apart, it accelerates until space-time itself can't hold. First, galaxy clusters would rip apart, then individual galaxies, stars, planets, and eventually atoms in a big rip event. The timeline, some estimates suggest as little as 20 billion years, a blink in cosmic terms. It's a haunting possibility that turns dark energy from a curious anomaly into a cosmic time bomb ticking in the void. Yet these theories barely scratch the surface of possibility. String theory proposes dark energy could be tied to compacted extra dimensions slowly unfurling. Others suggest we're seeing quantum gravity effects, a mirage caused by our incomplete understanding of how gravity operates across billions of light years. The wildest idea, that dark energy isn't a force at all, but an illusion created by our galaxy sitting in a rare, underdense region of the universe, like mistaking a local valley for global sea level drop. The stakes couldn't be higher. Dark energy doesn't just dictate how the universe expands, it writes the final chapter of existence itself. Will space thin into eternal ice as galaxies vanish over the horizon, collapse back into a singularity, or tear itself apart molecule by molecule? Every telescope pointed at distant supernova, every map of galaxy distributions is a vote in this cosmic referendum. And the strangest realization, the force deciding our fate might not even be a force at all, just a gap in the equations where reality hasn't bothered to explain itself yet. In the quiet static between radio stations, the universe occasionally screams a burst of energy so intense it outshines entire galaxies, then vanishes in less time than it takes to blink. These are fast radio bursts, or FRB, cosmic flashes that pack more power than 500 million suns into milliseconds. First discovered in 2007, these signals arrive from deep space without warning, often from billions of light years away, leaving astronomers scrambling to explain how something so brief can be so staggeringly powerful. The mystery only deepens when you look at the patterns. Some FRBs are one-off events, cosmic fireworks that flare once and never return. Others, like the famous repeater FRB 1211-2, fire off signals in unpredictable cycles like a lighthouse with a broken timer. This inconsistency has fueled wild speculation. Could these be messages from advanced civilizations or the death throes of exotic stars? The leading theory points to magnetars, ultra-dense neutron stars with magnetic fields so strong they warp atomic structures. Picture a stellar corpse spinning at breakneck speed, its crust cracking under magnetic pressure, releasing tsunamis of radio waves. Yet even this dramatic explanation struggles to account for the sheer energy some FRBs release. Then there's the question of distance. Many FRBs originate far beyond our galaxy, meaning their signals have traveled for eons before reaching us. As they pass through intergalactic dust and plasma, their wavelengths stretch and scatter, an effect that lets scientists measure the universe's hidden matter. But some bursts defy even this logic. In 2020, astronomers detected an FRB inside our own Milky Way, linked definitively to a known magnetar. While this confirmed a source for at least some bursts, it also raised new questions. Why do some magnetars produce FRBs while others stay silent? And why do certain bursts repeat while others vanish without a trace? The most tantalizing possibility: we might be seeing multiple phenomena lumped together under one name. Colliding neutron stars, evaporating black holes, or even cosmic strings, theoretical defects in spacetime, could all produce similar flashes under the right conditions. And yes, the alien hypothesis still lingers, though most scientists consider it a last resort. After all, as one researcher put it, it's probably not aliens, but we should check just to be sure. What makes FRBs so thrilling isn't just their mystery, but their potential as cosmic tools. Because they traverse vast cosmic distances, analyzing their signals could map the universe's invisible structure, the diffuse gas between galaxies that's nearly impossible to study otherwise. New telescopes like Canada's CHIME array are discovering FRBs by the dozens, each one a fresh clue in this interstellar detective story. Yet for every answer, a new question emerges. Why do some bursts show bizarre frequency patterns, like a radio dial spinning wildly? Could certain repeating FRBs be powered by orbital dynamics, a neutron star dancing too close to a black hole? The truth is, we're only beginning to eavesdrop on these cosmic screams. Each detection peels back another layer, revealing how much we still don't understand about the universe's most violent and fleeting phenomena. Whether they're magnetar tantrums, collapsing wormholes, or something beyond our current physics, one thing's clear: when the cosmos shouts, it doesn't bother to explain itself. Among the thousands of fast radio bursts detected so far, one stands out like a scratched record stuck on repeat: FRB 1211-2. Unlike most FRBs that flash once and disappear, this cosmic repeater has fired off hundreds of bursts since its discovery, each one a frantic blip of energy from a galaxy 3 billion light-years away. But here's what truly baffles scientists: its signals aren't random. They arrive in chaotic yet somehow structured patterns, like a drummer improvising to a rhythm only the universe understands. Some bursts cluster within minutes, then go silent for months. Others appear in predictable windows, as if whatever's producing them operates on a cosmic timetable we're only beginning to decode. The leading suspect, a magnetar, a city-sized neutron star with a magnetic field trillions of times stronger than Earth's. Picture a dying star so dense that a teaspoon of its material weighs 1 billion tons, spinning faster than a kitchen blender and crackling with magnetic energy. When these objects undergo starquakes, sudden fractures in their rigid crusts, they can unleash tsunamis of radio waves powerful enough to cross the universe. But FRB 1211-2 throws a wrench into this tidy explanation. Most magnetars calm down after a few violent outbursts, yet this source has been active for over a decade, suggesting something far more exotic might be at play. One theory points to a magnetar orbiting a supermassive black hole, its bursts distorted by the black hole's crushing gravity like a funhouse mirror. Another suggests a dense nebula of plasma swirling around the star, acting as a lens that magnifies and scrambles its signals. The wildest idea: that we're seeing the aftermath of a neutron star collision, a cosmic car crash that left behind a chaotic remnant still shedding energy like sparks from a grinding wheel. Each new observation adds layers to the puzzle, revealing details no single model can fully explain. What makes these repeating bursts so valuable is their consistency. Unlike one-off FRBs that vanish before we can study them, repeaters like 1211-2 let astronomers compare signals across years, hunting for subtle changes. Recent analysis revealed something startling. The bursts exhibit Faraday rotation, a twisting of radio waves that suggests they're traveling through an incredibly powerful magnetic field. This matches the environment around a magnetar, but the strength of the field is unlike anything we've seen in our own galaxy. It's as if this object is a magnetar on steroids, or perhaps something entirely new, a missing link between neutron stars and black holes. The most tantalizing clue came in 2022 when researchers noticed the bursts from 1211-2 sometimes arrive in two distinct flavors: bright, simple pulses and fainter, more complex ones. This bimodal pattern hints at two separate mechanisms at work, maybe a crackling stellar surface combined with swirling plasma clouds, or periodic eruptions from a debris field left by a shattered companion star. The more we learn, the clearer it becomes that FRBs aren't just cosmic oddities. They're Rosetta Stones for extreme physics, offering glimpses into environments where matter warps into forms impossible to recreate on Earth. Yet for all the progress, fundamental questions remain. Why do some magnetars produce FRBs while others lie silent? What determines whether a burst will repeat or vanish forever? And why does 1211-2's activity ebb and flow like tides on an alien shore? Upcoming telescopes like the Square Kilometre Array promise to detect millions more FRBs, mapping their origins across the cosmos. But for now, each burst from 1211-2 feels like a postcard from the edge of known physics, a reminder that even the universe's most fleeting signals can carry echoes of the extraordinary. The universe should be teeming with life, with hundreds of billions of galaxies, each containing trillions of planets orbiting in habitable zones. The numbers scream that we can't possibly be alone. And yet silence, no signals, no visitations, no cosmic neighbors dropping by. This glaring contradiction is the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody? If life is statistically inevitable, why does the cosmos feel so empty?" One terrifying answer lies in the concept of great filters, catastrophic barriers that prevent life from progressing to interstellar stages. Imagine civilizations as candles flickering in the dark. Some never ignite, planets too hostile for even simple life. Others burn briefly before snuffing out, wiped out by asteroid impacts, gamma-ray bursts, or their own self-destruction through war or environmental collapse. The haunting possibility: we might be alone not because life is rare, but because something keeps stamping it out before it can spread. If that filter lies ahead of us, some unavoidable doom like runaway artificial intelligence or nanotech plagues, then humanity's future could be tragically brief. But what if the filters are behind us? Some argue that the leap from simple cells to complex life is astronomically improbable, a fluke that took billions of years on Earth. Or perhaps intelligence itself is a dead end, an evolutionary aberration more likely to create dinosaurs than diplomats. Then there's the zoo hypothesis. Advanced civilizations know we're here but choose not to interfere, observing us like animals in a cosmic wildlife preserve. It's a comforting thought until you consider how rarely humans leave ecosystems undisturbed. Technology adds another layer of mystery. Our own radio signals have barely traveled 100 light-years, a tiny bubble in the Milky Way. An advanced species might communicate via neutrino beams or quantum entanglement, methods invisible to our primitive scanners, or they could have transitioned beyond physical forms, uploading consciousness into Dyson swarms or black hole computers, invisible to hunters of planetary biosignatures. Some theorists suggest we're searching the wrong scale. alien megastructures might not look like solid objects but subtle thermodynamic anomalies, their heat signatures hidden in plain sight. The darkest interpretation: we're early. The universe is 13.8 billion years old, but it's still in its infancy for star formation. Most habitable planets won't form for trillions of years, meaning we might be among the first life forms to ask these questions. Or the last. The Fermi Paradox isn't just about aliens, it's a mirror reflecting our own fragility. Every silent star is either a warning or a challenge, proof that survival isn't guaranteed, or an invitation to become the elders we hope to find. Perhaps the universe isn't silent, just indifferent. The zoo hypothesis suggests we're living in a cosmic preserve, deliberately isolated by advanced civilizations who watch from a distance but refuse to interfere. It's a scenario that feels equal parts comforting and unsettling. Humanity as an exhibit in some grand interstellar museum, our wars and art observed with detached curiosity. But if true, why build a zoo in the first place? Some theorize it could be an ethical choice, a way to avoid cultural contamination until we reach a certain technological maturity. Others speculate darker motives, like preserving us as a control group in a vast sociological experiment. Then there's the stealthy AI scenario, the idea that any civilization advanced enough to colonize the stars would inevitably create superintelligent machines, and those machines might have no interest in making contact with biological life. Think of it like ants trying to communicate with a supercomputer. The gap is too vast for meaningful interaction. These artificial intelligences could be all around us, harnessing black holes for energy or running simulations in hidden pockets of space-time, utterly indifferent to our primitive radio signals. Their infrastructure might even be invisible to us, disguised as natural phenomena or operating on scales our instruments can't perceive. SETI, the search for extraterrestrial intelligence, hasn't given up. They've just gotten smarter about where to look. Instead of scanning only for radio waves, modern efforts like Breakthrough listen hunt for laser pulses, neutrino bursts, and even Dyson sphere heat signatures, technosignatures that a stealthy or post-biological civilization might emit unintentionally. There's also the tantalizing possibility of detecting alien artifacts in our own solar system. Projects like Galileo aim to scan for interstellar objects that might be more than just rocks, probes, relics, or derelict tech drifting between stars. But the most radical shift: SETI is now listening for technofossils, signals from civilizations that burned bright and died long ago. The universe is 13.8 billion years old. Entire empires could have risen and fallen before Earth even formed. Their final broadcasts might still ripple through the void, red shifted into near silence. New algorithms sift through cosmic noise for these ghostly echoes, hunting not for hello messages but for cosmic obituaries. The truth might be humbler. Maybe spacefaring life is impossibly rare, or interstellar travel is a logistical nightmare no one solves. Or perhaps we're like islanders unaware of an ocean, missing the galactic internet because we're still using smoke signals. Whatever the answer, the Fermi Paradox remains a mirror. In searching for aliens, we're really asking, what does it mean to survive long enough to be found? On August 15, 1977, a radio telescope in Ohio picked up a signal so extraordinary that the astronomer who discovered it scrawled, "Wow," in red ink on the printout, a cosmic exclamation that would name one of astronomy's most enduring mysteries. For 72 seconds, the Big Ear telescope recorded a narrowband radio burst 30 times stronger than background noise, pulsing at exactly 1,420 megahertz, the frequency hydrogen absorbs and emits light, a natural choice for any civilization trying to announce its presence. Then, just as suddenly as it appeared, the signal vanished, never to repeat despite decades of searching. What makes the WOW signal so tantalizing isn't just its intensity, but its fingerprint. The signal's bandwidth matched what scientists predicted an artificial transmission would look like, too narrow to be natural, yet too powerful to be earthly interference. It originated from the direction of the constellation Sagittarius, near a star cluster 1,800 light-years away, though no known celestial object in that region could produce such a focused emission. Satellite signals, military transmissions, both were ruled out. The telescope's design made hoaxes nearly impossible, and the signal's frequency drifted slightly, as it would from a source moving with Earth rotation, exactly what you'd expect from a distant extraterrestrial beacon. Theories range from the plausible to the fantastical. Some suggest we caught a one-time event, an alien equivalent of a lighthouse beam sweeping past Earth for an instant. Others propose it was a reflected human signal bouncing off space debris, though nothing in orbit at the time matched the profile, the darkest possibility. That it was a genuine call from the stars, sent by a civilization that fell silent before we could answer. Imagine shouting into a canyon and hearing a reply just once, a voice echoing from the cliffs before the valley goes quiet forever. Modern telescopes like the Allen Telescope Array have scanned the same patch of sky thousands of times, hunting for a repeat. Artificial intelligence now sifts through radio noise for similar patterns, yet the original signal remains stubbornly unique. Some astronomers argue it might have been a comet's hydrogen cloud glinting in the sun, an idea that gained traction when researchers noted 2 comets were near the detection zone in '77. But critics point out comets don't emit narrowband signals, and their trajectories didn't align precisely enough to explain the data. Perhaps the most haunting aspect is the timing. The WOW signal appeared during a brief listening window when Big Ear happened to be pointed at just the right slice of sky. Had the telescope been offline that night or aimed a few degrees elsewhere, we'd never have known it existed. It's a reminder that the cosmos might be shouting all around us, but we're only catching fragments of the conversation. Whether it was a fleeting cosmic coincidence or the universe's cruelest tease, the WOW signal endures as proof that sometimes the most profound mysteries arrive without explanation and leave without a trace. Some stars flicker gently like candles in the wind, but then there's Tabby's star, a cosmic strobe light flashing secrets we still can't decipher. Officially catalogued as KIC 8462852, this unassuming star 1,200 light-years away in Cygnus behaves like nothing else in the known universe. Most stars dim by fractions of a percent when planets pass by. Predictable, rhythmic dips in brightness. Tabby's star, it plunges by up to 22% at random intervals, sometimes for days, sometimes for weeks, as if something vast and jagged is drifting across its face. And when astronomers checked century-old photographic plates, they found something even stranger. The star's overall light output appears to have dropped by 14% over the past 100 years. Stars don't just fade like that unless something is deliberately blocking the light. Theories erupted faster than solar flares. The initial explanation, a swarm of comets, quickly unraveled. To cause such extreme dimming, you'd need millions of giant comets packed tighter than bees in a hive, a scenario with odds so slim it makes winning the lottery look inevitable. Then came the megastructure hypothesis, the notion that an advanced civilization might be building a Dyson swarm around the star, harvesting its energy with orbiting solar panels or habitats. Imagine a vast constellation of artificial objects, each blotting out starlight as they pass, a concept that sent telescopes scrambling for answers, but even this sci-fi scenario hit snags. Subsequent studies found the dimming affects all wavelengths equally, which dust-free megastructures shouldn't do. Nature, it seems, is taunting us with a puzzle that defies both mundane and extraordinary explanations. What makes Tabby's star so electrifying isn't just the mystery, it's how every new observation deepens the intrigue. In 2021, astronomers caught it dimming rapidly over just a few days with no accompanying heat signature. Dust, the usual culprit for such behavior, should glow in infrared when blocking starlight. Yet Tabby's star dims without a thermal trace, as if whatever's passing in front is utterly cold or deliberately engineered to absorb all wavelengths. Some researchers now suspect we're seeing the aftermath of a planetary collision, a cosmic car crash that left behind a debris field of asteroid-sized fragments. Others propose a natural but never-before-seen phenomenon, a ringed giant planet with sprawling, uneven rings eclipsing the star at chaotic angles. The most tantalizing clue came from studying the star's flickers in polarized light. When light passes through dust grains, it becomes polarized, a telltale sign of ordinary cosmic debris. But Tabby's star's light shows no such polarization, suggesting the obstructing material isn't dust at all. It's as if we're staring at a stage where the props keep changing, but the magician refuses to reveal the trick. Even now, telescopes monitor it relentlessly, hoping to catch another dramatic dimming event that might finally crack the case. Perhaps the greatest lesson from Tabby's star is how much we still don't know about stellar behavior. For all our catalogs of exoplanets and galaxy maps, the cosmos still holds phenomena that leave astronomers wide-eyed and reaching for new physics. Whether it's a swarm of shattered worlds, a cosmic optical illusion, or something far stranger, one thing's certain: this star refuses to follow the script. And that's what makes it irresistible, a celestial rebel reminding us that the universe always keeps a few cards hidden. Most of space is crowded with galaxies, swirling in clusters like schools of fish in an endless ocean. But in the constellation Boötes, there's a place where the ocean runs dry, a spherical void so vast it could hold 60 Milky Ways side by side with room to spare, yet contains almost nothing. This is the Boötes Void, a cosmic desert stretching 330 million light-years across, where galaxies are so sparse that if you stood at its center, the night sky would appear nearly black. Discovered in 1981 by astronomer Robert Kirshner, this void defies expectations. Based on our understanding of cosmic structure, a region this empty shouldn't exist, or at least it shouldn't be this empty. At first glance, you might think it's just a statistical oddity, a random bubble in the froth of the universe where matter didn't clump together, but the numbers don't add up. Simulations of the cosmos predict voids, yes, but none this enormous and empty. The Boötes Void holds roughly 60 galaxies that we've detected so far. That sounds like a lot until you realize a region that size should contain at least 2,000. It's as if someone took a cosmic vacuum and sucked away 98% of the galaxies, leaving behind only scattered stragglers. What's even stranger, the galaxies that do remain aren't clustered together like survivors huddling in a storm. They're spread out like lonely outposts in an unimaginably vast wasteland. One theory suggests the void might be the result of smaller voids merging over billions of years, like soap bubbles combining into one enormous emptiness. Another proposes it's evidence of an ancient collision with a parallel universe, a wild idea rooted in speculative physics, where our cosmos bumps against another in higher dimensional space, leaving behind scars like this. Then there's the unsettling possibility that the void isn't empty at all. It could be filled with dark matter so dense it stifled galaxy formation, or even with rogue black holes drifting unseen. The most chilling hypothesis, that an advanced civilization somehow engineered this emptiness, harvesting galaxies on a scale we can barely comprehend. Yet the truth might be simpler and far more profound. The Boötes Void could be forcing us to rethink how structure forms in the universe. Recent studies hint that voids might play an active role in shaping cosmic expansion, their emptiness creating gravitational repulsion that pushes galaxies apart faster than expected. If true, this void isn't just a hole. It's an actor in the universe's grand play, sculpting the cosmos in ways we're only beginning to grasp. Every telescope pointed at its darkness brings back new questions. Why do the few galaxies inside it spin differently than their counterparts outside? Could their unusual motion be a clue to the void's origins? One thing's certain, the Boötes void isn't just empty space. It's a mirror reflecting how much we still don't understand about the universe's architecture. For all our maps of galaxy clusters and dark matter webs, this gaping absence reminds us that the cosmos still holds puzzles too big to ignore and answers that might lie not in the light but in the darkness between. When NASA Pioneer 10 and 11 spacecraft sailed beyond the orbits of Jupiter and Saturn, they carried with them humanity's first physical messages to the stars' gold plaques etched with symbols of our existence. But as these intrepid probes ventured farther from Earth, they began transmitting data that would baffle scientists for decades. Despite precise calculations predicting their trajectories, both pioneers experienced an inexplicable deceleration, an unseen force tugging them back toward the sun with a gentle but persistent pull. This tiny anomaly, barely 1/10,000th the strength of Earth's gravity at their distance, shouldn't have existed according to Newton's laws, yet there it was year after year, accumulating into a deviation of hundreds of thousands of miles from where the probe should have been. At first, researchers suspected mundane explanations: fuel leaks, instrument errors, even the gravitational influence of undiscovered Kuiper belt objects. But as other deep space missions like Galileo and Ulysses exhibited similar, though less pronounced deviations, the Pioneer anomaly became impossible to ignore. The effect was achingly consistent, an unmodeled acceleration of approximately 8.74 times 10 to the minus 10 meters per second squared, acting toward the sun. For scale, that's like feeling a grain of sand's weight gently pressing against your hand in space, but over interplanetary distances it added up. The leading explanation finally emerged years later: thermal recoil force. As the plutonium-powered Pioneers generated heat, their radioactive decay warmth radiated unevenly from the spacecraft bodies. Picture a teapot cooling heat escapes in all directions, but if one side reflects more than the other, the net push can create thrust. In the Pioneers' case, infrared emissions bouncing off their dish antennas might have generated just enough backward pressure to explain the anomaly. Detailed analysis of heat distribution models seemed to confirm this until researchers noticed inconsistencies. The thermal explanation could only account for about 60% of the observed deceleration, leaving a stubborn remainder unaddressed. Doubt lingers because other spacecraft built differently, like the New Horizons probe now racing through the Kuiper belt, haven't shown the same effect with comparable precision. This suggests the Pioneers' unique design, with their heat-producing RTGs mounted behind large parabolic antennas, played a role. But here's the catch: even after accounting for every conceivable thermal variable, some residual anomaly persists. Could there be an undiscovered systemic error in how we model deep space navigation? Or might this hint at something more profound, a flaw in our understanding of gravity itself? Some theorists proposed radical solutions, like modified gravity models that tweak Einstein's equations at extremely weak accelerations. Others looked to dark matter interactions or even subtle space-time curvature effects from the sun's rotation. The most tantalizing and controversial idea: that we're glimpsing the edge of known physics where quantum mechanics and general relativity might intersect in unexpected ways. The Pioneers' whisper-thin deceleration could be the first tremor of an earthquake in cosmology. What makes this mystery endure isn't just the unresolved physics, it's the lesson it teaches about exploration. Sometimes the greatest discoveries come not from the dramatic events, but from the faintest anomalies, the tiniest deviations in data that refuse to vanish. The Pioneers' plaques may one day be found by alien civilizations, but their true legacy might be this: that even our best engineered missions can become cosmic questions, drifting through the dark with answers just out of reach. On October 19, 2017, astronomers spotted something streaking through our solar system that shouldn't have been there, a visitor from another star. Named Oumuamua, Hawaiian for scout or messenger from afar arriving first, this interstellar object defied every expectation. Most comets and asteroids follow predictable paths shaped by gravity and the gentle push of solar radiation. But Oumuamua didn't just sail past the sun, it accelerated, as if something invisible was propelling it forward. The anomalies started with its shape. Instead of the rough, lumpy profile of typical asteroids, radar observations suggested Oumuamua was flat, like a pancake or a cigar, tumbling end over end through space. Then came the real shock, its trajectory. After slingshotting around the sun, Oumuamua sped up slightly, an effect usually seen in comets when their icy surfaces vaporize, creating a natural rocket effect. But Oumuamua showed no signs of outgassing, no telltale coma of gas and dust, no icy tail. It was as if this thing had an engine but no exhaust. Scientists scrambled for explanations. Maybe Oumuamua was a cosmic iceberg, made of hydrogen or nitrogen so pure that its sublimation left no visible trace. Or perhaps solar radiation pressure alone could account for its acceleration, though that would require an object impossibly thin, like a sheet of paper floating on the solar wind. The more data we gathered, the stranger it became. Spectroscopic analysis revealed no water ice, no carbon-rich molecules, just a reddish surface baked by eons of cosmic rays. Then came the wild card hypothesis. Could Oumuamua be artificial? Astronomer Avi Loeb famously suggested it might be a light sail, a piece of alien technology drifting between stars propelled by starlight itself. The idea ignited fierce debate. Critics argued that extraordinary claims require extraordinary evidence, and Oumuamua's quirks, while bizarre, could still have natural origins. Supporters countered that dismissing the possibility outright risked blinding us to potential breakthroughs. After all, if we found a smartphone in medieval Europe, would we assume it was a strangely polished rock? The truth is, we may never know. Oumuamua is now beyond the reach of our telescopes, vanishing into the void as silently as it arrived. But its legacy lingers, a reminder that the universe is capable of throwing curveballs we don't yet have the physics to catch. Whether it was a shard of a shattered planet, a new class of interstellar object, or something even more unimaginable, one thing's certain: the next time a visitor like this streaks through our neighborhood, we'll be watching far more closely. Imagine holding a map of the universe's infancy, a snapshot of the cosmos when it was just 380,000 years old, glowing with the afterbirth of the Big Bang. This is the cosmic microwave background, or CMB, the oldest light we can see, stretched into microwaves over 13.8 billion years of expansion. It should be random, a chaotic tapestry of hot and cold spots scattered like spilled paint. But when scientists peeled back the layers, they found something that shouldn't be there, an eerie alignment between this ancient light and the plane of our solar system. They called it the axis of evil, not because it's malevolent, but because it threatens one of cosmology's most sacred principles. The cosmological principle states that on large scales, the universe should look the same in all directions, no preferred axis, no special location. Yet the CMB's temperature fluctuations seem to whisper otherwise. The warmer patches trace a path that suspiciously aligns with our solar system's ecliptic, as if the universe somehow knew where we'd be standing billions of years later. It's like finding fingerprints on a fossil that perfectly match your own. Statistically, the odds of this happening by chance are less than 1 in 1,000, a fluke so improbable it keeps cosmologists awake at night. Some dismissed it as an observational error, a ghost in the data from satellites like Planck or WMAP. Others dug deeper, finding that certain large-scale structures, galaxy clusters, quasars, even the polarization of the CMB itself also share this peculiar alignment. The implications are staggering. If the universe has a preferred direction, it undermines the very foundation of modern cosmology. maybe we're seeing the fingerprints of a pre-Big Bang structure, a cosmic fingerprint left by whatever birthed our universe. Or perhaps it's evidence that we're embedded in something larger, a bubble universe among countless others in a multiverse, each with its own unique physics. The wildest theories suggest the axis of evil might be a relic of quantum entanglement from the universe's first moments, a frozen echo of connections that once bound everything together. Others propose it's a sign of rotational symmetry in the early cosmos, a spin so vast it imprinted itself on spacetime, but the most unsettling possibility. That we're seeing the limits of our models, a crack in the cosmological principle wide enough to drive a multiverse through. Every new map of the CMB sharpens the mystery. The axis of evil isn't just a curiosity, it's a cosmic riddle that could rewrite our place in the universe. Whether it's a statistical mirage, a flaw in our telescopes, or a glimpse beyond the edge of known physics, one thing's certain: the cosmos has a way of humbling us just when we think we've got it figured out. And sometimes the most unsettling discoveries aren't about what's out there, but what our inability to explain them says about how much we still don't know. Beneath the smooth fabric of space and time we perceive lies a chaos so violent it makes ocean storms look tranquil, a seething, bubbling froth known as quantum foam. Picture the surface of a boiling lake, where bubbles form and burst in trillionths of a second, but instead of water, this turbulence twists the very structure of reality itself. At scales a billion times smaller than an atom, spacetime isn't the serene continuum Einstein described. It's a writhing maze of tiny wormholes, virtual particles, and black holes blinking in and out of existence so fast they defy measurement. This is the frontier where gravity and quantum mechanics collide, and our understanding of physics shatters like glass. The wildest implication: this foam might be warping light from distant stars without us even realizing it. When photons travel billions of light years across the cosmos, they don't glide through empty space, they're battered by this invisible quantum storm. Some researchers argue these spacetime bubbles could subtly bend high-energy gamma rays, like a flashlight beam flickering through a swirling fog. The catch: detecting this effect would require instruments precise enough to measure distortions smaller than an atom over interstellar distances. Our most advanced telescopes are laughably crude by comparison. It's like trying to hear a whisper across a hurricane. Why can we prove quantum foam exists? The math paints a clear picture, but reality refuses to cooperate. To observe spacetime's froth directly, you'd need a particle accelerator the size of the Milky Way, or a microscope powered by energies comparable to the Big Bang. Even the concept of observing breaks down here. The act of measurement requires energy, and at these scales, the energy needed would create more quantum foam, distorting the results like a hall of mirrors. It's the ultimate cosmic catch-22. The tools that could prove the foam's existence are rendered useless by the foam itself. Some theorists suggest we're asking the wrong questions altogether. Quantum foam might not be a static phenomenon but a dynamic one, fluctuating in ways that erase any trace of its existence the moment we try to pin it down. Others propose that what we call empty space is actually a hologram, a projected illusion where foam-like turbulence in higher dimensions translates into the three-dimensional reality we perceive. The most radical idea, that spacetime isn't fundamental at all, but emerges from something far stranger, like a cosmic quantum computer running the universe's code. Yet for all its elusiveness, quantum foam leaves fingerprints where we least expect them. The very fact that light from distant quasars arrives in such crisp, focused beams hints that spacetime's turbulence might be smoother than predicted, or that it operates by rules we haven't yet imagined. Every mystery in modern physics, from dark energy's repulsive force to the paradoxes of black holes, loops back to this bedrock question: what is space really made of? Until we crack that code, the foam will keep slipping through our fingers, a reminder that the universe's greatest secrets don't hide in the distant cosmos, but in the fabric beneath our feet. Black holes were supposed to be the universe's ultimate shredders, cosmic traps where anything that crossed the event horizon vanished forever, leaving no trace of what fell in. Then Stephen Hawking dropped a bombshell in 1974. Black holes aren't black, they glow. Tiny, faint, but undeniably there. This glow, now called Hawking radiation, meant black holes could slowly evaporate, fading into nothingness over trillions of years. But here's the catch. If a black hole disappears, what happens to all the information about the stars, planets, and unlucky astronauts it swallowed? According to quantum mechanics, information can't be destroyed. It must persist, even if scrambled beyond recognition. Yet Hawking's math suggested it was vanishing into oblivion. This contradiction, the black hole information paradox, has been tearing physics apart for 50 years. The heart of the problem lies in a fundamental clash between quantum theory and gravity. Quantum mechanics treats information like an indestructible currency. It can change forms but never disappear. Think of burning a book. The ashes seem meaningless, but in theory, every word could be reconstructed from the smoke particles' quantum states. But black holes, governed by Einstein's gravity, appear to erase this information permanently. Hawking radiation, it turns out, isn't carrying any fingerprints of what fell in. It's just random thermal noise, so when the black hole finally evaporates, the information seemingly vanishes too, a violation of quantum law that would force us to rewrite the rules of reality. Enter the firewall paradox, a desperate solution that feels more like science fiction than physics. If information can't escape a black hole but can't be destroyed either, maybe it piles up at the event horizon like a cosmic traffic jam, creating a raging wall of energy that incinerates anything approaching. Imagine diving toward a black hole expecting smooth sailing, only to hit a barrier hotter than the sun's core the instant you cross the threshold. It's an elegant fix, but it comes with a price, tossing out Einstein's principle that free falling into a black hole should feel uneventful, like floating through empty space. The holographic principle offers a way out, one where the information isn't lost but encoded. Picture a black hole's event horizon as a two-dimensional surface, like the security hologram on a credit card. Everything that falls in gets smeared across this surface in quantum bits, preserved forever like a cosmic hard drive, the three-dimensional objects we see plunging into the abyss. Just projections of that data, illusions created by the horizon's pixel-like structure. When Hawking radiation escapes, it slowly decrypts this information, carrying it back into the universe. It's as if the black hole isn't a pit but a hall of mirrors, where reality is both inside and on the surface at the same time. Yet even this mind-bending idea has cracks. If information leaks out via Hawking radiation, it should create subtle correlations between particles emitted at different times, a quantum handshake we've yet to detect. Some theorists argue the paradox hints at something deeper, that spacetime itself is emergent, stitched together by quantum entanglement like a cosmic tapestry. In this view, the paradox isn't a problem to solve but a clue that we're missing a fundamental layer of reality. The stakes couldn't be higher. If information truly vanishes in black holes, it undermines quantum theory's core, and with it, everything from chemistry to computing. If firewalls exist, Einstein's relativity needs patching. And if holograms are real, we might be living in a universe far stranger than we ever dreamed. The paradox isn't just about black holes, it's a battle for the soul of physics, forcing us to ask, is reality as we know it just a shadow of something far deeper? Until we crack this puzzle, black holes will keep whispering secrets we can't yet understand, their mysteries locked behind a horizon of unanswered questions. The moon hangs in our sky as a silent witness to Earth's history, a cratered companion we've walked upon, sampled, and studied for decades. But beneath its dusty surface lies a puzzle that defies expectations, the ghost of a magnetic field. Today, our moon is a magnetically dead world, its core too small and cold to generate the swirling currents needed to power a planetary dynamo. Yet lunar rocks tell a different story, preserving traces of an ancient magnetic field nearly as strong as Earth. How could this be, and why did it vanish so completely? Samples brought back by Apollo astronauts contain tiny magnetic signatures locked in their mineral grains, like fossilized compass needles pointing to a time when moonwalks would have required magnetized boots. Analysis reveals this field thrived around 3 to 4 billion years ago, peaking with an intensity roughly 1% of Earth's current magnetism before flickering out like a dying ember. The numbers don't add up. For a magnetic field that strong, the moon's core should have been churning with vigorous convection, yet its modest size suggests it cooled rapidly after formation. Picture trying to keep a campfire burning with just a handful of twigs. It shouldn't have lasted nearly as long as it did. One theory points to a gravitational dance with Earth. Early in its history, the moon orbited much closer to our planet, and tidal forces may have stretched and flexed its interior like putty, generating enough heat to keep the core molten. Computer simulations show this lunar dynamo could have been powered by mechanical stirring rather than conventional convection, a magnetic engine driven by motion rather than temperature alone. But here's the catch: tidal heating should have faded as the moon drifted outward, leaving the core to solidify. Yet the magnetic field persisted for nearly 1 billion years after this mechanism became inefficient, as if something else took over. That something might lie buried in the moon's mantle. Recent studies suggest massive sinking slabs of crystallized magma could have periodically jump-started the dynamo. As these dense lunar rocks plunged toward the core, they might have displaced hotter material upward, creating temporary currents that rejuvenated the magnetic field like a failing battery given one last surge of power. Supporting this, some Apollo samples show magnetic spikes occurring in distinct episodes rather than a steady decline, hinting at fits and starts rather than a slow fade. Then there's the impact hypothesis. The young moon endured a bombardment of asteroids so violent it reshaped entire basins. These collisions could have delivered enough energy to superheat the mantle, driving convection through sheer brute force. Imagine striking a bell, not with a steady rhythm, but with random, world-shaking blows that kept the core ringing with each hit. Some researchers argue this explains why the magnetic record is so chaotic, with spikes corresponding to periods of intense cratering. The most tantalizing clue comes from tiny metallic grains in lunar soil. Under extreme magnification, their crystal structures reveal a history of rapid cooling, evidence that the moon's field didn't just fade gradually, but collapsed suddenly in geological terms, possibly within just a few 100 million years. This abrupt shutdown suggests a catastrophic change, like the core crystallizing all at once or a massive impact disrupting its flow beyond recovery. Whatever happened, it left the moon as we see it today, a silent, unmagnetic world holding onto secrets older than life itself. Solving this mystery isn't just about lunar history. It's a key to understanding how small rocky worlds lose their magnetic shields, a process that dictates whether they can protect atmospheres or nurture life. As NASA prepares to return astronauts to the moon, new core samples and seismometers could finally crack the case. Until then, those magnetized rocks remain cosmic crime scene evidence, whispering of a time when the moon wasn't just a dead companion, but a dynamic world with a magnetic heartbeat all its own. At the North Pole of Saturn, a storm rages unlike any other in the solar system, a perfect hexagon wider than 2 Earths, spinning like a cosmic gear for decades without faltering. This 6-sided behemoth, first glimpsed by Voyager in the 1980s and later studied in stunning detail by Cassini, defies everything we know about planetary weather. Storms don't form geometric shapes, they churn chaotically, their edges ragged and unpredictable. Yet here's Saturn's hexagon, its razor-sharp angles holding firm as jet streams howl at over 300 kilometers per hour, a structure so precise it looks engineered. What keeps this atmospheric oddity locked in place? Laboratory experiments here on Earth might hold the key. When scientists filled a circular tank with spinning water, a simplified model of Saturn's polar atmosphere, something remarkable happened. At certain speeds, the fluid spontaneously organized into polygons, including a near-perfect hexagon. The secret lay in the shear between different layers of motion. On Saturn, where the planet's deep atmosphere rotates at varying speeds, similar turbulence could be carving that six-sided shape into the clouds like an invisible lathe. But there's a catch. Earth-based models can't replicate the scale or persistence of Saturn's hexagon. Our tiny water tanks produce fleeting shapes that dissolve in seconds. Saturn's storm has endured for at least 40 years, possibly centuries. The hexagon's stability points to something deeper, literally. Saturn's interior churns with layers of metallic hydrogen, a form of matter so compressed it behaves like a liquid metal, generating the planet's immense magnetic field. Some researchers suspect this roiling inner ocean interacts with the atmosphere above, creating stable wave patterns that rise through thousands of kilometers of gas to imprint themselves on the cloud tops. Think of it like a colossal tuning fork vibrating at a frequency that just happens to produce six sides. Then there's the wild card, Saturn's seasons. Unlike Earth's modest axial tilt, Saturn leans at 27 degrees, subjecting its poles to decades-long cycles of sunlight and darkness. As the hexagon basked in continuous summer light during Cassini's mission, its colors shifted from blue-gold to golden haze, hinting at chemical changes in its towering cloud walls. Yet through it all, the hexagon held its shape, untroubled by the shifting sunlight. This resilience suggests the structure is rooted far below the weather layer, anchored by forces we've yet to measure. The most haunting question isn't just how the hexagon forms, but why it's unique. Jupiter's poles swirl with chaotic cyclones. Neptune and Uranus boast violent wind shears. Yet nowhere else in the solar system does nature draft such perfect geometry. Could Saturn's deep rotation rate, a brisk 10-hour day, be the magic ingredient? Or does its intricate ring system play a role, casting gravitational shadows that stabilize the polar vortex? One thing's certain, the hexagon is more than a curiosity. It's a laboratory for extreme physics, a place where the rules of fluid dynamics stretch to their breaking point. As future missions dream of diving through Saturn's upper atmosphere, this shimmering six-sided enigma remains a beacon, a reminder that even the best understood laws of nature still hold secrets written in the clouds of distant worlds. We think we know where most of the ordinary matter in the universe should be: the protons, neutrons, and electrons that make up everything from stars to smartphones. After all, this baryonic matter is what we're made of, what our telescopes are built to detect. But here's the cosmic accounting error that's kept astrophysicists scrambling for decades. When they tally up all the visible matter in galaxies, clusters, and gas clouds, nearly half of it is missing. Not hidden as dark matter, not transformed into energy, just gone. Like balancing a checkbook where 40% of the money has vanished without a paper trail. The prime suspect, an elusive, superheated web of gas stretched between galaxies, so diffuse it's nearly invisible. Scientists call it the warm-hot intergalactic medium, WIM for short. Picture the universe's scaffolding not as empty space, but as a sprawling network of threads, each one a river of million-degree plasma too thin to glow like a star, yet dense enough to hide trillions of suns worth of material. Detecting this ghostly structure is like trying to spot a fog bank from 10,000 feet. It's everywhere, but you need exactly the right tools to see it. X-ray telescopes offered the first clues. When trained on distant quasars, the brilliant cores of active galaxies, they found strange dips in the light. Not the sharp cuts of solid objects, but subtle, wavy absorption lines, as if the quasar's light had passed through a cosmic haze. These fingerprints matched highly ionized oxygen, a telltale sign of gas heated to hundreds of thousands of degrees. The catch, the signal was so faint it barely rose above the noise. To confirm WIM existence, astronomers needed to catch it red-handed, not just in absorption but in emission, its own faint glow. Enter modern cosmology's most patient hunters, ultraviolet spectrographs aboard satellites like Hubble and Fuse. By stacking countless observations of the same patch of sky, they've begun teasing out WIM whisper-thin ultraviolet emission. The results are staggering filaments stretching hundreds of millions of light-years, containing up to 50% of the universe's missing baryons. But this gas isn't just lounging in space, it's dynamic, cycling in and out of galaxies like a cosmic breathing system. Supernova and black holes blast it outward, while gravity slowly pulls it back, creating a hidden circulatory system that fuels star formation across epochs. The most tantalizing evidence comes from the cosmic microwave background. Tiny temperature fluctuations in this ancient light reveal how ordinary matter was distributed when the universe was just 400,000 years old. Fast forward to today, and simulations show that same matter should have collapsed into the vast cosmic web we now detect with the WIM as its connective tissue. The numbers finally align, but the story isn't complete. We're still missing about 30% of the baryons, likely hiding in even harder to detect forms, cooler gas clumps or low-density regions between filaments. New telescopes like ESA's Athena mission aim to solve this once and for all, using ultra-sensitive X-ray detectors to map the WIM in 3D. Meanwhile, radio astronomers are hunting for faint hydrogen signals redshifted into oblivion by the expanding universe. It's a painstaking chase, but the payoff would rewrite our understanding of cosmic structure. After all, these missing baryons aren't just accounting errors. They're the hidden reservoirs that determine how galaxies grow, how stars ignite, and ultimately, how the universe built the conditions for us to exist. The WIM may be nearly invisible, but its fingerprints are everywhere, woven into the very fabric of space itself. Yet the mystery deepens when we consider scale. Some of this missing matter might not even be in filaments. It could be floating as ultra-diffuse clouds in the voids between galaxy clusters, so sparse that each cubic meter holds just a few atoms. Others speculate about dark galaxies, massive but starless structures where baryons cooled into cold gas without ever igniting. The universe, it seems, has a knack for hiding its ingredients in plain sight, forcing us to rethink not just where we look, but how we define what's findable. This isn't just a cosmic scavenger hunt. It's a reality check. For all our advanced technology, we're still learning how much of the universe resists easy detection. The missing baryons remind us that ordinary matter can be just as elusive as the dark variety when it's strewn across the void in forms we're only beginning to comprehend. Every time we close one gap in the cosmic ledger, another opens, proving that even the stuff we're made of still holds surprises. The WIM isn't just hiding matter, it's hiding the answers to how the universe organizes itself on the grandest scales. And when we finally map its full extent, we won't just solve a puzzle, we'll uncover the invisible architecture shaping everything we see. The universe is expanding, that much we've known since Hubble's groundbreaking observations nearly a century ago. But how fast? That's where the plot thickens, because depending on where you look or how you measure, you'll get two very different answers. This discrepancy, known as the Hubble tension, isn't just a minor rounding error. It's a full-blown crisis in cosmology, forcing scientists to question whether we've misunderstood the cosmos on a fundamental level. On one side, there's the local measurement, using pulsating stars called Cepheid variables and exploding supernova as cosmic yardsticks. Astronomers calculate an expansion rate of roughly 73 kilometers per second per megaparsec. Picture a galaxy 3.3 million light-years away. It should be racing outward from us at 73 kilometers every second. But peer deeper into the universe's past using the cosmic microwave background, the afterglow of the Big Bang, and the rate drops to 67. That 6-kilometer gap might sound trivial, but over cosmic distances, it adds up to a chasm between competing visions of reality, the weirdest part. Both methods are rock solid in their own right. Cepheids are gold standard distance markers, their pulsations so predictable we've used them to map the universe for over a century. And the cosmic microwave background, it's the most precise snapshot of the infant cosmos we've got. Its fluctuations etched into space when the universe was just 380,000 years old. Neither camp is sloppy, both have triple-checked their math, so why can't they agree? Some theorize we're missing a piece of physics, an unknown form of dark energy that briefly surged in the universe's adolescence, throwing off the CMB's predictions. Others propose that dark matter interacts with itself in ways we haven't accounted for, subtly altering how structures formed. Then there's the unsettling possibility that the Hubble constant isn't constant at all. That expansion rates vary across space, making our local neighborhood unrepresentative of the whole. Imagine measuring the speed of rivers worldwide, but only sampling ones near mountains. You'd miss the slower flows of the plains. The stakes couldn't be higher. If the tension persists, it might mean our standard model of cosmology, the meticulously crafted recipe of dark matter, dark energy, and ordinary stuff we've relied on for decades, is incomplete. Perhaps gravity behaves differently on cosmic scales, or the universe isn't as homogeneous as we assumed. The wildest idea, that we're seeing echoes of a sibling universe brushing against ours in some higher dimensional space, warping expansion in ways we can't yet explain. New telescopes like the James Webb Space Telescope are diving into the fray, scrutinizing Cepheids and supernova with unprecedented precision. Early results. They're only deepening the mystery, confirming the local rate with even tighter margins of error. Meanwhile, next-generation CMB experiments like the Simons Observatory aim to remeasure the universe's baby pictures with finer detail. But until someone finds a smoking gun or a flaw in our assumptions, the Hubble tension remains a glaring rift in our understanding of cosmic evolution. What makes this clash so thrilling isn't just the disagreement, it's what it reveals about how science grapples with the unknown. Sometimes the universe doesn't give tidy answers. Sometimes it hands you two exquisitely precise measurements that refuse to reconcile, forcing you to dig deeper, question harder, and wonder if the real discovery isn't the discrepancy itself, but whatever lies beyond it. The Hubble tension isn't a problem to solve, it's a doorway, and on the other side might be a universe far stranger than we ever imagined. Beyond the orbit of Neptune, where sunlight weakens to a dim glow, the Kuiper belt stretches like a frozen junkyard of ancient cosmic debris. This vast ring of icy bodies follows predictable patterns until it doesn't. Around 50 astronomical units from the Sun, something bizarre happens. The number of detectable objects plummets as if sliced by an invisible blade. Astronomers call this abrupt boundary the Kuiper cliff, and it makes no sense. Based on our models of solar system formation, the belt should continue relatively unchanged for hundreds of gradually thinning like salt scattered on a table. Instead, it's as if someone built a cosmic fence at 50, leaving the yard beyond suspiciously empty. One compelling theory suggests the cliff marks the gravitational footprint of a hidden world, an undiscovered planet lurking in the darkness. Not necessarily the hypothetical Planet 9, but perhaps a smaller, closer perturber whose orbit sweeps the region clean like a celestial snowplow. Mathematical simulations show that a Mars-to-Earth-sized object orbiting between 60 and 100 could explain the sudden drop-off, its gravity shepherding smaller bodies into tighter clusters or flinging them into the abyss. The challenge, spotting such a distant world, is like searching for a charcoal briquette in a pitch-black basement. Even our most powerful telescopes struggle to detect cold, dark objects at those distances unless they cross in front of a background star by pure chance. Yet the planet hypothesis isn't the only game in town. Alternative explanations dig into the solar system's violent adolescence. Billions of years ago, during the era of planetary migration, Neptune may have rampaged outward from its birth orbit, plowing through the Kuiper belt like a bulldozer. This chaotic period could have ejected countless objects into interstellar space, leaving behind a sharply defined edge where the devastation stopped. Supporting this, some computer models show that Neptune's migration would naturally sculpt a cliff-like boundary, though matching it precisely to 50 requires fine-tuning that leaves astronomers uneasy. Then there's the wild card, interstellar interference. Our sun didn't form in isolation. It was born in a dense stellar nursery alongside thousands of sibling stars. A close pass by another star early in the solar system's history could have stripped away the outer Kuiper belt like a thief swiping the outer layer of a wedding cake. The timing would have to be impeccable, early enough to shape the belt but late enough to avoid disrupting the inner planets. While statistically unlikely, the universe has a way of serving up improbable events when we least expect them. The most tantalizing clue lies in the peculiar orbits of objects just inside the cliff. Some Kuiper belt residents like Sedna and 2012 VP 113 follow extreme, elongated paths that tilt wildly out of the solar system's plane, as if something massive yanked them off course. These outliers behave like cosmic breadcrumbs, tracing a trail that might lead to whatever carved the cliff in the first place. Upcoming surveys like the Vera Rubin Observatory's decade-long scan of the southern sky could finally spot the culprit, whether it's a stealthy planet or evidence of a long, close stellar encounter. What makes the Kuiper cliff so unnerving isn't just the mystery. It's the realization that even in our own cosmic backyard, there are borders we don't understand. The solar system doesn't just fade into the void, it ends in puzzles. Whether the answer is a hidden world, a violent past, or something even stranger, one thing's clear: the edge of the known is never where we think it is. And beyond that cliff, the darkness might be hiding more than we ever imagined. High above the horizon, just before dawn or after dusk, when the sky is neither fully dark nor lit by the sun's direct glare, a faint triangular glow sometimes rises from the direction of the sunrise or sunset. This ethereal light, known as the zodiacal light, has been observed for centuries, a soft pyramid of radiance formed by sunlight scattering off trillions of dust particles drifting through the inner solar system. For decades, astronomers assumed this dust came from comets and asteroid collisions, a steady rain of debris left over from the solar system's formation. But recent measurements have revealed something unsettling. The zodiacal light is far brighter than it should be. According to our best models of asteroid breakup rates and comet dust production, there simply shouldn't be enough material out there to account for the glow we see. The math just doesn't add up. When researchers tally the known sources of interplanetary dust collisions in the asteroid belt, crumbling comets, even micrometeoroid grinding, they come up short by a factor of 2 or more. It's as if someone secretly dumped an extra truckload of glitter into the solar system's inner regions. Where is all this excess dust coming from? One tantalizing possibility points to Mars. The planet's thin atmosphere and frequent dust storms might be lofting fine particles into space, where solar radiation pressure could spread them along the ecliptic plane. But even this can't fully explain the anomaly. The sheer volume of missing dust suggests a more prolific source, something actively replenishing the reservoir on timescales we haven't yet accounted for. Then there's the dust's mysterious distribution. The zodiacal light isn't uniform. It contains strange clumps and asymmetries that defy simple explanations. Infrared surveys have detected dense bands of dust trailing certain asteroid families, while other regions appear suspiciously devoid of particles. Some researchers argue this patchiness hints at recent catastrophic collisions, events like the breakup of a large asteroid within the past few 100,000 years, showering the inner solar system with fresh debris. Others propose a more dynamic process, gravitational resonances with Jupiter acting like a cosmic broom, herding dust into specific orbital zones while clearing others. The most radical theory, we might be seeing the aftermath of an unseen population of dark comets, icy bodies that don't develop visible tails but steadily shed material as they sneak through the inner solar system. These stealthy snowballs could be peppering the zodiacal cloud with dust at rates far higher than traditional comets, their contributions overlooked because they don't announce themselves with brilliant tails. Supporting this idea, surveys have begun spotting more of these Manx comets, objects with comet-like orbits but no visible outgassing. If they're more numerous than we thought, they could be the hidden engines of the zodiacal dust factory. What makes this mystery so compelling isn't just the missing dust, it's what solving it could reveal about the solar system's hidden activity. The zodiacal light isn't static. It's a living record of ongoing processes, a fog of debris that traces everything from asteroid collisions to planetary weather. Each particle carries forensic clues about its origins, and by mapping their collective glow, we're essentially reading the solar system's diary, one written in light scattered off dust grains too small to see individually, but together painting a puzzle we're only beginning to decode. Upcoming missions like JAXA Destiny Plus aim to fly through this dust cloud, analyzing its composition in situ. What they find could rewrite our understanding of how small bodies evolve and interact. For now, the zodiacal light remains a beacon of the unknown, a gentle glow that shouldn't be as bright as it is, whispering of processes and events we've yet to discover. Every time it appears in the twilight sky, it's not just a celestial phenomenon. It's a reminder that even in the well-mapped territories of our own cosmic neighborhood, surprises still lurk in the light. The cosmic microwave background is often called the universe's baby picture, a near-perfect snapshot of the cosmos as it was just 380,000 years after the Big Bang. But like any family photo, there's an oddity lurking in the frame. Stretching across a patch of sky in the constellation Eridanus, there's a region so cold it defies explanation. A cosmic cold spot spanning nearly 1.8 billion light-years where the CMB's temperature drops by a hair, raising 70 microkelvins. That might sound minuscule, but in the grand thermal symphony of the early universe, it's a discordant note loud enough to make cosmologists question everything. At first glance, the culprit seems obvious, a supervoid. These sprawling cosmic deserts, devoid of galaxies and dark matter, could theoretically cool photons passing through them via the integrated Sachs-Wolf effect. Imagine light climbing out of a gravitational well, losing energy along the way like a cyclist pedaling uphill. If the cold spot sits atop an especially vast void, its chill would make perfect sense. But here's the problem: when astronomers mapped the region with galaxy surveys, they found nothing big enough to explain the temperature drop. The voids we've spotted are mere puddles compared to the oceanic emptiness required. It's as if we found a freezer in the desert but no power source to run it. This discrepancy has fueled wilder theories. Some physicists propose the cold spot is a bruise from a collision with another universe, a multiverse remnant pressed into our cosmos like a fingerprint in clay. According to bubble universe theory, our cosmos might be one of countless others floating in an eternal cosmic foam, each with different physical laws. If one of these bubbles grazed ours during inflation, the energy exchange could have left behind a localized chill in the CMB. The math is speculative but tantalizing. Certain models show such collisions would indeed create disk-like cold regions with precise temperature profiles eerily similar to what we observe. Yet the multiverse explanation isn't without skeptics. Critics argue it's a theory of anything, an idea so flexible it can't be disproven. Others point to subtle statistical quirks, the cold spot's temperature profile isn't quite as crisp as collision models predict, and its surrounding hot rings are fuzzier than they should be. Then there's Occam's razor, the principle that the simplest solution is often correct. Could the cold spot just be a statistical fluke? After all, in a universe with infinite random fluctuations, even a 1 in 10,000 anomaly is bound to crop up somewhere. The plot thickens when you examine polarization data. If the cold spot were truly a supervoid, it should leave distinct polarization patterns in the CMB's light. Initial Planck satellite measurements found hints of these fingerprints, but later analyzers questioned their significance. It's as if the universe is teasing us with half-clues, revealing just enough to keep the mystery alive. Meanwhile, alternative explanations keep bubbling up. One recent study suggested the cold spot might be the shadow of a cosmic texture, a hypothetical defect in space-time structure left over from the universe's violent birth. These knots in the fabric of reality would distort light in ways that mimic cooling, leaving behind ghostly imprints. What makes this debate so thrilling isn't just the scientific stakes, it's the philosophical undercurrent. Confirming a multiverse collision would revolutionize our understanding of reality, proving we're part of something infinitely larger. On the other hand, uncovering a new cosmological effect within our own universe could be equally transformative, revealing processes we've never imagined. Future telescopes like the Simons Observatory aim to scrutinize the cold spot with unprecedented precision, hunting for the faint polarization signals that could break the deadlock. Until then, this icy anomaly remains one of cosmology's most tantalizing Rorschach tests, a cosmic Rorschach blot where some see voids, others see multiverses, and the truth might be stranger than either. Imagine a form of matter so strange that it doesn't just break the rules, it rewrites them entirely. Enter unparticles, a hypothetical substance that behaves unlike anything in the standard model of physics. If ordinary matter is an orchestra playing in perfect harmony, unparticles are the cacophony of a broken radio existing in a state that defies conventional categories of particles or waves. Proposed in 2007 by physicist Howard Georgi, this bizarre concept emerged from the fringes of theoretical physics, suggesting that at certain energy scales, matter might stop acting like discrete particles and instead blur into something far more exotic. The key to unparticles lies in scale invariance, a property where objects look the same no matter how much you zoom in or out. Think of a coastline. Whether viewed from space or through a microscope, its jagged edges appear similarly complex. Unparticles take this idea to the extreme, lacking the quantized properties that define particles like electrons or quarks. Instead of having a fixed mass or spin, they exhibit fractional behaviors as if stuck between dimensions. Picture a cloud of smoke that doesn't disperse but also never settles, occupying a ghostly middle ground between existence and abstraction. What ties this to the real world? Dark matter. Despite decades of searching, we've yet to pin down what makes up 85% of the universe's mass. Unparticles offer a tantalizing alternative to traditional candidates like WIMP or actions. Because they interact weakly, if at all, with ordinary matter, they could permeate galaxies invisibly, their collective gravity sculpting the cosmos without ever leaving a trace. Some models suggest unparticle-mediated forces might even explain dark matter's elusive nature, creating subtle tugs between galaxies that mimic the effects of unseen mass. Yet for all their promise, unparticles remain speculative, a beautiful mathematical idea lacking experimental proof. Detecting them would require spotting infinitesimal energy discrepancies in particle collisions or observing anomalies in the way gravity bends light around galaxies. So far, no such signals have emerged. Critics argue that without direct evidence, unparticles risk joining the graveyard of elegant theories undone by reality. But supporters counter that their very strangeness makes them worth pursuing. After all, the universe has a habit of being weirder than we imagine, the deeper implication. If unparticles exist, they'd hint at a hidden sector of physics, a shadow realm operating by rules we've yet to decipher. It's like discovering a secret layer to reality, one where the familiar laws of quantum mechanics and relativity are just the surface. For now, the unparticle hypothesis remains a thrilling thought experiment, a reminder that some of science's greatest leaps begin with asking, what if the impossible isn't? Whether it's the key to dark matter or a dead end in the quest to understand the cosmos, one thing's certain: the universe loves to keep us guessing. Galaxies aren't supposed to disobey the rules, especially not one as seemingly ordinary as NGC 1052 DF2. At first glance, this ultra-diffuse galaxy looks like any other, a smattering of stars, some globular clusters drifting quietly in the cosmos. But when astronomers measured its rotation in 2018, they stumbled upon something impossible. The stars in this galaxy were moving far too slowly for the amount of visible matter present. In other words, there was no trace of the dark matter halo that should have been holding it together. The discovery sent shockwaves through cosmology because this wasn't just a missing piece of the puzzle, it was a piece that shouldn't have existed in the first place. Dark matter is the universe's invisible scaffolding, making up 85% of all matter. It's the reason galaxies spin faster than they should and cluster in ways visible matter alone can't explain. Every galaxy we've studied, from massive spirals to tiny dwarfs, has shown signs of being wrapped in this enigmatic substance until NGC 1052 DF2. Without dark matter's gravitational glue, its stars should have flown apart long ago, like a merry-go-round spinning so fast it flings riders into the air. Yet here it is, stable and serene, mocking our understanding of how galaxies form. The immediate suspicion was that we'd made a mistake. Perhaps the distance measurements were off, throwing off calculations of the galaxy's mass. Or maybe dark matter was present but hiding in a form we couldn't detect. Follow-up observations only deepened the mystery. The Hubble Space Telescope confirmed the galaxy's distance, ruling out measurement errors. Its globular clusters, usually reliable tracers of dark matter, were moving at sluggish speeds, confirming the absence of unseen mass. Even more baffling, NGC 1052 DF2 wasn't alone. A handful of other galaxies, like NGC 1052 DF4, also showed suspiciously low dark matter content. Were these cosmic oddities or signs of something bigger? One theory points to a violent past. NGC 1052 DF2 resides near a massive elliptical galaxy, NGC 1052, which could have ripped away its dark matter through gravitational interactions. Picture a thief in the night, stealing the invisible scaffolding and leaving behind a skeleton of stars. Simulations show this is possible. A close encounter with a larger galaxy might strip dark matter while leaving visible matter relatively unscathed. But there's a catch. The process should leave visible scars like tidal tails or distorted shapes, yet NGC 1052 DF2 appears eerily undisturbed. Another possibility is that dark matter and stars somehow became decoupled during the galaxy's formation. Maybe the dark matter was blown away by fierce galactic winds, or perhaps the galaxy formed in a freak collision where gas fragmented into stars without the usual dark matter backdrop. The wildest idea, that these galaxies are the first evidence of alternative gravity theories, like modified Newtonian dynamics, which eliminate the need for dark matter entirely by tweaking how gravity works on cosmic scales. But MAND has its own problems, failing to explain phenomena like the bullet cluster, where dark matter's gravitational fingerprint is unmistakable. Now the plot grows even stranger. Some researchers argue NGC 1052 DF2 isn't a galaxy at all, but a rare tidal dwarf, a splash of stars cast off during a galactic collision, born without dark matter from the start. Others suggest its dark matter might have been heated to such high energies that it evaporated, leaving no trace behind. The most unsettling implication: if galaxies can exist without dark matter, does that mean dark matter isn't as universal as we thought, or worse, that we've been misinterpreting its role altogether? As telescopes like James Webb and the upcoming Vera Rubin Observatory turn their gaze to these oddballs, the stakes couldn't be higher. Either these galaxies are cosmic rarities, flukes of nature that test the limits of our models, or they're the first cracks in the foundation of modern cosmology. For now, NGC 1052 DF2 floats in quiet defiance, a reminder that even the most fundamental rules of the universe might have exceptions waiting to be discovered. Black holes swallow everything: light, matter, even time itself without a trace. But what if the universe has a cosmic rewind button? Enter white holes, the hypothetical opposites of black holes, where nothing can enter and matter and energy only explode outward. Imagine a black hole played in reverse, a rupture in space-time where the universe violently exhales what it once inhaled. The math allows for this. Einstein's equations, which predict black holes, also permit white holes when you run the variables backward. Yet for all their theoretical elegance, these cosmic geysers have never been spotted. So are they more than just a trick of the numbers? The concept isn't as far-fetched as it sounds. In fact, one of the most tantalizing candidates for a white hole might be lurking in our telescopes already. Back in 2006, the SWIFT satellite detected a gamma-ray burst unlike any other Tabby 060614. Instead of fading in milliseconds like typical bursts, it flashed for nearly 100 seconds with a light curve that looked less like an explosion and more like a door slamming shut in reverse. Some theorists suggested this could have been a short-lived white hole, a brief portal where a black hole's interior momentarily turned inside out. The energy profile matched predictions: a sudden, violent ejection of trapped radiation from a singularity that had somehow reversed its own collapse. But here's the catch: no similar event has been observed since, leaving Tabby 060614 as a cosmic one-off, a fleeting maybe in the data. Then there's the quantum angle. Black holes evaporate over eons via Hawking radiation, slowly leaking energy until they vanish. But what happens at the very end? Some models suggest the dying ember of a black hole could rebound into a white hole, a final burst of space-time recoiling from total collapse. Picture a deflating balloon suddenly reinflating, except the balloon is a singularity, and the air is all the information it ever swallowed. This Planck star hypothesis offers a potential solution to the black hole information paradox, ensuring data isn't lost but instead regurgitated in a fiery rebirth. The problem: these white holes would be microscopic, lasting fractions of a second, their faint signals drowned out by the cosmic background. Skeptics argue white holes are nothing more than mathematical artifacts, flukes that appear when you stretch relativity to its limits without accounting for quantum mechanics. After all, entropy and thermodynamics favor disorder, and a white hole's pristine outflow defies the universe's preference for chaos. Then again, so did black holes once, until we found them lurking in the hearts of galaxies. Perhaps white holes aren't stable structures but transient events, flickering into existence at the edge of spacetime before collapsing under their own impossibility. The wildest possibility: white holes could be the birth cries of other universes. Loop quantum gravity, a contender for unifying relativity and quantum physics, suggests that when a black hole collapses, the immense density at its core might trigger a bounce, spawning an infant universe in a separate branch of spacetime. From our perspective, this would look like a white hole, a point where another cosmos bleeds into ours. It's a dizzying thought. Every black hole in our universe could be the umbilical cord to a new one, with white holes as the fleeting moments of connection. Yet for now, white holes remain phantoms, shadows cast by the equations we trust to describe reality. Whether they're waiting to be discovered or destined to stay as thought experiments, they force us to confront a humbling truth. the universe has a habit of turning our wildest speculations into facts and our surest truths into puzzles. After all, if black holes teach us anything, it's that the cosmos loves a good paradox, and if white holes are real, they might just be the ultimate cosmic joke, a universe that eats its secrets only to spit them back out when we least expect it. At the edge of our observable universe, in the constellation Eridanus, there's a place where the cosmos seems to forget itself, a yawning abyss so vast it could swallow 10,000 Milky Ways without a trace. This is the Eridanus supervoid, a billion light-year stretch of near-nothingness that isn't just empty but unnaturally cold. When astronomers first mapped the cosmic microwave background, the afterglow of the Big Bang, they expected minor temperature fluctuations, the universe's equivalent of static. But this void registered a chilling 70 microkelvins colder than its surroundings, as if someone had left a cosmic freezer door ajar. What makes this supervoid so unsettling isn't just its size, it's the fact that it shouldn't exist in such pristine form. According to our best models of cosmic structure, voids this enormous are statistical impossibilities, like finding a desert the size of a continent with not a single grain of sand out of place. The math suggests the odds of a void this large and cold forming naturally are less than 1 in a million. Either we've witnessed a one in a birth of the universe fluke, or there's something fundamentally wrong with how we understand the cosmos. One leading theory suggests the void acts like a cosmic decompression chamber. Photons traveling through it lose energy as they climb out of its shallow gravitational well, a phenomenon called the integrated Sachs-Wolf effect. But here's the catch. For this to explain the temperature drop, the void would need to be far emptier than any structure we've observed. Galaxy surveys show it's not devoid of matter entirely, just sparsely populated like a ghost town with a few dim streetlights still flickering. That leaves a glaring gap between what we see and what the models demand. Alternative explanations venture into wilder territory. Could the supervoid be the imprint of a collision with another universe? Some multiverse theories predict that neighboring bubbles in the cosmic foam might occasionally brush against each other, leaving behind telltale cold spots. Others propose it's evidence of a cosmic defect, a scar from when spacetime itself crystallized asymmetrically in the early universe, like ice forming cracks as it freezes. The most radical idea, that we're seeing the shadow of a higher dimensional structure warping our reality from beyond the observable universe, yet skeptics counter that the void might not be as special as it seems. The human brain excels at finding patterns, even where none exist, a phenomenon called apophenia. Could this just be a case of cosmic pareidolia, where random fluctuations happen to align in a way that looks significant? Detailed statistical analyses suggest otherwise. The cold spot's temperature profile matches predictions for a genuine supervoid, not a random noise artifact. And its position offset from the plane of our galaxy rules out Milky Way interference. The plot thickens when you examine the void's neighbors. Surrounding galaxies show peculiar velocities, as if they're being gently repelled by the void's emptiness. This dipole repeller effect hints that the supervoid isn't just a passive hole, but an active player in the cosmic web, subtly influencing the motion of nearby galaxies like a gravitational negative space. Future telescopes like the Vera Rubin Observatory aim to map these motions with unprecedented precision, potentially revealing whether the void's pull is as anomalous as its chill. What's at stake isn't just one oddball region of space, it's our entire understanding of how the universe structures itself. If the Eridanus supervoid is real and not a statistical mirage, it could force us to rewrite the rules of cosmic inflation, dark energy, or even the nature of gravity itself. Perhaps it's a cosmic Russian nesting doll, with smaller voids stacked inside larger ones in a fractal pattern we've yet to decode. Or maybe it's a signpost pointing toward physics beyond our current theories, a silent reminder that the universe's greatest mysteries aren't always written in light, but sometimes in the absence of it. As we peer deeper into this cosmic cold spot, one thing becomes clear: the void isn't empty. It's full of questions, and the answers, when they come, might rewrite not just the story of this one strange corner of the cosmos, but the entire narrative of how we fit into it. What if everything around us, the stars, the laws of physics, even your thoughts right now, weren't real, but lines of code in an unfathomably advanced simulation? The simulation argument isn't just science fiction. It's a serious hypothesis debated by physicists and philosophers, grounded in eerie cosmic coincidences and quantum behaviors that feel more like glitches than features of reality. Think about the double-slit experiment, where particles behave as waves or particles depending on whether we observe them, like a video game rendering graphics only when a player looks. Or consider Planck length, the smallest possible unit of space, suggesting the universe might be pixelated at its core, a cosmic resolution limit hinting at underlying programming. The math even offers unsettling odds. If future civilizations could run ancestor simulations, high-fidelity recreations of their past, the number of simulated minds would dwarf the number of biological ones. Statistically, you're more likely to be one of those simulated beings than a flesh and blood human. Even Elon Musk has quipped, the odds we're in base reality are 1 in billions. But the clues go deeper. Quantum entanglement, where particles instantly influence each other across vast distances, defies locality in a way that feels optimized, like a simulation skipping unnecessary calculations until observed. Then there's the Fermi Paradox. If the universe is so vast, where are all the aliens? Unless, of course, the simulation's parameters were set to keep civilizations isolated, saving processing power. Skeptics counter that the argument is a modern-day brain-in-a-vat thought experiment, provocative but untestable, yet some scientists are actively seeking proof. One team proposed looking for computational rounding errors in high-energy cosmic rays, tiny inconsistencies that might reveal the universe's frame rate. Others suggest that if space-time is pixelated, we might detect its resolution limit in the blurring of distant starlight. The wildest idea, that glitches in quantum behavior, like particles briefly violating energy conservation, could be patches in the simulation's code, hotfixes for unexpected bugs. The implications are dizzying. If we're in a simulation, do the programmers interact with us? Are black holes data garbage collectors? And what happens if we ever crack the code? Some philosophers warn that proving we're simulated could trigger an existential crisis, while others see it as liberation, a chance to hack the system. For now, the mystery remains open, a cosmic joke where the punchline might be written in binary. Whether we're players or NPCs, one thing's certain: the universe's greatest secret might not lie in the stars, but in the possibility that someone, somewhere, is staring at a screen watching us figure it out. From the silent pull of the Great Attractor to the phantom glow of Hawking radiation, from the cosmic scream of fast radio bursts to the hexagonal storm raging on Saturn, we've journeyed through 25 of the universe's most baffling enigmas. And yet, here's the humbling truth: this is just the tip of the cosmic iceberg. For every mystery we've uncovered, there are 1,000 more lurking in the shadows, waiting to rewrite our understanding of reality. The void isn't empty, it's a canvas of unanswered questions, each one a reminder that the universe delights in keeping secrets. Think about it: dark matter tugs at galaxies without showing its face. Dark energy pushes the cosmos apart with no explanation. The Wow signal teases us with a one-time whisper from the void, while Tabby's star flickers like a broken streetlight in the cosmic neighborhood. And let's not forget the Boötes void, a billion light-year stretch of nothingness that shouldn't exist. These aren't just gaps in our knowledge, they're invitations to explore further, to question deeper. What's astonishing isn't just the scale of these mysteries, it's how they defy our intuition. Black holes shouldn't glow, yet they do. The moon shouldn't have had a magnetic field, yet it did. The Pioneer probes drifted off course in ways physics can't fully explain, while Oumuamua accelerated without a trace of a comet's tail. Even our own solar system holds puzzles like the Kuiper Cliff's abrupt edge or the zodiacal light's unexplained brightness. The more we learn, the clearer it becomes. The universe is a master of the unexpected, and that's the beauty of it. Science isn't about having all the answers, it's about chasing the next question. Maybe you're captivated by the simulation hypothesis, wondering if we're all lines of code in some grand cosmic program. Or perhaps the Fermi Paradox keeps you up at night, pondering why the stars are so silent. Whatever mystery resonates with you, one thing's certain: the cosmos isn't done surprising us. So let's keep looking, let's keep wondering. After all, the greatest discoveries often start with the simplest question: what if? Now it's your turn. Drop your favorite cosmic enigma in the comments, and who knows, maybe the next big breakthrough will begin with a conversation right here. The universe is vast, the mysteries are endless, and the adventure, it's just getting started.